From pairs we build a world of thought, of functions rule a path we sought. Equivalents for grouping, orders for ranking, each elements find its spot. Relations link the mind to heart, a logical and elegant art.
Previously, we defined the image and preimage of a function and studied some examples. In this section, we will use those definitions to prove a few basic properties. Let f be a function from a to b, c a subset of a, and d a subset of b. We recall some statements that follow directly from the definitions of image and preimage. First, if x is in C, then fx is in the image of C. Second, if y is in the image of C, then there exists some x in C such that fx equals y. Third, if fx is in D, then x is in the preimage of D. Last, if x is in the preimage of D, then fx is in D. Most of the proofs of the properties ahead are just combinations of the above statements. Let f be a function from a to b, with C1 and C2 subsets of A and D1 and D2 subsets of B. We first prove the monotonicity for images. If C1 is a subset of C2, then the image of C1 is a subset of the image of C2. To see this, let y be an arbitrary element of fc1. This means that y equals f of x for some x in C1. But since C1 is a subset of C2, this x lies in C2 as well, so its function value fx is in fc2. Thus, f of C1 is contained in f of C2. Similarly, we can prove that if D1 is a subset of D2, then the preimage of D1 is a subset of that of D2. To this end, let x be an arbitrary element of the preimage of D1. Then fx is in D1, and hence in D2 since D1 is a subset of D2. This implies that x belongs to the preimage of D2 and proves the property. Next, we study how images and preimages behave under set operations, starting with the preimages. Let f be a function from a to b with D1 and D2 subset of b. The preimage of a union is equal to the union of the preimages. To see this, take an arbitrary x in A. Then x is in the preimage of the union if and only if fx is in the union of D1 and D2, which is equivalent to either fx being in D1, in which case x is in the preimage of D1, or fx being in D2, in which case x is in the preimage of D2. In other words, x is in the union of the preimages. Since the arguments in each step are reversible, we have proved the desired set equality. With similar arguments, we can prove that the preimage of an intersection is equal to the intersection of the preimages, and that the preimage of a difference is equal to the difference of the preimages. We leave it to the audience to check the details. Now let us consider the analogues for images. For unions, the union of the images is equal to the image of the union. This follows by a similar argument as in the case of preimages, and we leave it to the audience as an exercise. Things become more tricky for intersections and set differences. First, the image of an intersection is always contained in the intersection of the images. To see this, let y be an arbitrary element of the image of C1 intersecting C2. Then y equals fx for some x in the intersection of C1 and C2. Since x is in C1, fx is in the image of C1. Similarly, since x is in C2, fx is in the image of C2. Thus y is in the intersection of the images of C1 and that of C2. For set differences, a similar argument shows that the image of C1 taking off the image of C2 is contained in the image of C1 taking off C2. To see this, let y be an arbitrary element in the image of C1 taking off the image of C2, then y is in the image of C1, and hence equals fx for some x in C1. Note that this x cannot be in C2, otherwise fx would be in the image of C2, contradicting our assumption. Therefore, x is in C1, taking off C2, while y is in its image. We remind the audience that in general, these two subset relations cannot be upgraded to equalities. To see this, consider the function f from 0, 1 to itself, sending both 0 and 1 to 1. Let C1 be 0 and C2 be 1, then the intersection of C1 and C2 is the empty set, whose image is again empty, while the intersection of the images is the singleton one. Similarly, let C1 be 0, 1 and C2 be 0. Then the image of C1 and the image of C2 are both the singleton one, producing the empty set as their set difference, whereas the image of C1 minus C2 is the singleton one and is not empty. Finally, we study a mixture of image and preimage. Let f be a function from a to b, let c be a subset of a, and let d be a subset of b. The image fc is a subset of the codomain b, so we can consider its preimage. Similarly, the preimage of d is a subset of the domain a, so we can consider its image. We have the following properties. For any subset C of A, the preimage of the image of C contains C, and for any subset D of B, the image of the preimage of D is contained in D. Again, the proof of these propositions depends only on the definitions. For the first property, let C be a subset of A, and let X be an arbitrary element in C. Since X is in C, we have Fx in Fc. As a result, X is in the preimage of Fc. For the second property, let Y be an arbitrary element in the image of the preimage of D. Then Y equals Fx for some X in the preimage of D. But X being in the preimage of D implies that Fx is in D, hence Y is in D. To convince yourself that the subsets can be proper subsets, consider the previous example. Let C be the singleton 0 in the domain. Then the image of C is the singleton 1, whose preimage is the set 0 and 1, which is not equal to C. On the other hand, let D be the singleton 0 in the codomain. Its preimage is empty, which remains empty after taking its image, and is thus a proper subset of D. Indeed, as we will see in the future, to upgrade these inclusions to equalities, we need injectivity for the first one and surjectivity for the second one.
신라 텐세